Yeah, I kept the asymptotics portion to the last class just to give her more chances to prepare. And if she wants to present, she can present her like a recent paper, because it's also related to asymptotics. But we did some congruences last time, and we will do congruences once again. We will prove the same terms once again, but this time using Colbert's method. Using like we will get the witness identity. That's the name. Yeah. So we prove these two congruences. So Ramanujan's congruences for the number of partitions. So P of n is the number of partitions. P of 5n plus 4. Ramanujan observed that this is always divisible by 5, and it is a crazy result that you get a number from the additive number theory world, and it satisfies a divisibility problem, like property, and there's no obvious reason why it should be. Because I mean, these numbers are just like, we don't even have a closed formula for them, but somehow it satisfies this arithmetic property that all of these coefficients, when you jump in the steps of 5, are divisible by 5. And same thing, 7n plus the next number 5, that is congruent to 0 modulo 7. And we proved these two. And then Ramanujan observed one more, which is 11n plus 6 is congruent to 0 mod 11. So to prove these things, we needed to use a lot of like corollaries of Jacobi triple product identity, and the corollaries that we used were that one of them was Euler pentagonal number theorem, which we have done many months ago. So I write it with x. Yeah, let's write it with x. So it is x sub infinity, or this product 1 minus x to the m, where m from 1 to infinity is the sum, bilateral sum from negative infinity to infinity, negative 1 to the k, q to the 3, k to the power 2, minus k, or plus k, it's the same thing. Just take k to negative k, it will be the same thing, over 2, right? This was one of them. And the other variant that we needed was the cube of this. So x sub infinity cube, which is wherever you want to put that cube. I will put it here this time, but there gets cube from 1 to infinity. And this is not a bilateral sum this time. So it is k greater or equal than 0 to infinity. And that is negative 1 to the k, 2k plus 1, and q x. It should also be x here too. We always use q when we're counting stuff, but whenever we're doing some analysis, they just change x for not necessarily good reason. So it is k squared minus k over 2. Or k squared plus k over 2. Yeah, this is the triangle of numbers. It's k plus 1 choose 2. So it is k plus 1 choose 2. So we needed these two. And we will still need these two. But before, when we were dealing with that, we took the original function. We took the original like 1 over xx sub infinity, which was the sum pn xn. Then we shifted that one. So we multiplied it with x so that we get this x minus 1 here. So that 5n plus 5n plus 4 came with x to the 5n type coefficient. So it came with the exponents of x being divisible by 5. So we multiplied it with x, which made, among a lot of things, these 5n plus 4 things to come with x to the 5n plus 5s. Right? Then we identified like these coefficients. We identified like what these coefficients can be, or like if they satisfy some sort of divisibility, using that this being divisible by 5. So that was our tag. That's how we pulled these coefficients out. And we will do pretty much the same thing, but this time, instead of proving it this way, we will prove an identity for the generating function. And that is, we will prove that if you were to take these 5n plus 4 coefficients and tag them along the x to the n, So I have a sift. So instead of the whole generating function and then trying to identify things, I take only these coefficients that I'm interested in, and I know, or I hope that they're divisible by 5. So I will get a witness identity that says that this definitely has a factor of 5 plus some more stuff, which is like this e of x5 to the 5. I will define what e is. It is just a basic definition, e of x to the 6. And e is this guy. So depending on which school of thought you're coming from, there might be many different notations for this cubohammer symbol. But in this, I'll just call it an E. But I mean, as you can see, if we can prove this, and this is our goal for today. If we can prove that, it says that any coefficient, any number for partitions in the form of Pn plus 4, for the numbers of the form Pn plus 4, must have a factor of 5 inside. So it is the same as proving that. Right? It already has the factor 5 and maybe some other stuff. And this is why it's called a witness identity. So it witnesses like that there's a factor of 5 in these things. So yeah, for this, we will just need to play with these two sums and the generating function here somehow and get a formula for that. All right. So let's recap and define something. So we said e to the x is, e of x is this sum, 1 minus x to the m, and from 1 to infinity. We have this h of x, which is the cube of that, the ex cube, and it is the sum -1 to the n, 2n plus 1, and q, not qx, x. I'm so accustomed to writing cubes. X to the n squared plus n over 2, and n from 0 to infinity. And let's say p of x is the sum of these p of n's and x to the n's and greater or equal than 0. Okay. And one more, that is the g. That's the g that we need. That's the earlier contacted number there. So this is e of x, but I'm writing it as a sum. So it is n from negative infinity to infinity, -1 to the n, x to the power 2 minus n over 2. Fine. Cool. Now, after all, we want to not. Oh, my internet connection is unstable. Let's hope that it will be better. Yeah, I'm recording so that people can watch it as well. But I think it's okay. So this happened before. Yeah. So after all, we don't care about the full Pn. We care about the portion where we actually have this 5n plus 4, right? So that's what we're going to do. We will just say, you know what? Let's split this into pieces with respect to the modular class S, modular class 5, and the residue class is S. So let me write it with a different color. So we have it. So here's let me put a PS. It is 5m plus S, and the coefficients are, the exponents of x are 5m plus S. So we split our normal original function into 5 pieces. This is the S, I'll just put it that way, the purple ones, and the modulus class is 5. Let's do the same thing here too. So h of s, we want to split things. So it is the same deal, but now I just want this triangular number, n squared plus n divided by 2, to be congruent to s modulo 5. So I'm making a dissection into 5 pieces. When you sum them up, it becomes the original like full function, right? And here as well, so g of s, same deal. Take this exponent, 3n squared minus n divided by 2 is congruent to s modulo 5. Which is basically what we did last time as well, but we did it all together. Like we first just kept all the H's, P's, G's all together. We did the multiplication first. And at the very end, we tried to figure out what exponents of, what combination of exponents of X was making it 0 modulo 5. So we were doing the extraction at the very end. So this time we're just doing the extraction from the get-go. We have 5 H functions for 5 residue classes modulo 5, 5 P functions for the residue classes modulo 5, and 5 G functions. Okay. And as we have already observed, if you were to take the sum of these P functions, for example, PS of X, from S being 0 to 4, there are 5 of them after all, it is the normal, the whole generating function, which is this E of X. I'm really just dissecting it into 5 pieces. I'm not dissecting it correctly into 4 pieces. So this is the piece of the partition function. So when I sum up the partition function, what it should be is 1 over E of X, right? It should be the 1 over XX sub infinity. That gives me the generating function for partitions. But if we sum up the GS, we get the Euler pentagonal number theorem. And this one is actually the E of X. Right? Just dissections, nothing really special. If you were to sum up this HS, let's do that as well. If you were to sum up these HS functions together, no new ingredient yet. This is again the cube that we know the formula for. So it is E of X, but with a cube. Cool. And the ideas are the same. Again, we want to, after all, dissect the 0 modulo 5 case, because I mean, 0 modulo 5 is where we're going to have what we want, or like this S modulo 5 is what we want to get. So let's define one more function, which is this capital S of residue class R of X. And that is just this multiplication. So G of S and P of T, where S plus T is congruent to R modulo 5. Well, why are we doing that? Because I mean, it's actually simple. If you look at these two, when I multiply these two sums, the product is actually 1. Right? So over here, we will also be able to like identify what some pieces of this thing is. A little bit technical. I know I will try to keep it light. But the idea is when we have the full generating function for partitions and when we have the full Euler pentagonal number theorem, their product is just 1. Cool. So this product at the very bottom, which is exactly 1, has all these products that SR might have, right? It's actually a matrix multiplication, if you will. So maybe we can identify some stuff for these SRs. So let's write like what they are. And see, so S plus T. P of S, no, G of S, P of T. Let me keep it the same way. So G of S, P of T, P of T, and creates both X. So this is congruent to R modulo 5, S plus T is R modulo 5. We already said that the sum of PTs is this 1 over X infinity. Sum of GS is this X infinity. So their product is 1. And yeah, the sum of PS, sum of GS or GT is equal to 1. So these are all the information that we need for now. So let's look at the pieces of that. If I were to write down G of 0, S of 0, sorry, what would be the product? I would need all the S plus T's to be 0 modulo 5. I need all these combinations. So one of them is like I can have G of 0 and P of 0, P of 5. So you add the sub-indices, it is 0 modulo 5, sums up to 0. Plus I can have G of 1 and P of 4, right? G of 2, P of 3. Then another one is G of 3, P of 2. Oh, I'm pressing the button. P of 2 and G of 4 plus G of 4, P of 1. That's true. Yep. Thank you. And these are all the combinations, right? Is there any other combination? Remember that these are going from 0 to 4. The sums are going from 0 to 4. Is there any other combination which would give me 0 modulo 5 in the residual class? Okay, this is all the combinations. So let's write S of 1 as well. So G of 1, P of 0, G of 2, P of 4. So I'm just shifting everything once. G of 3, P of 3, G of 4, P of 2, and G of 0, P of 1. I want to write all of them so that we see that it's actually a matrix. So this is G of 2, P of 0, G of 3, P of 0, G of 4, P of 0. So this is S2, S3, S4. Let me quickly saturate this board. So it is G3, G4, G5, the same piece. 4, then G4, G0. So this is G0 anyway. G5, G0 are the same thing. G1. So this is P3, P3, P3 plus this is 4, 0, P2. Then it's a G1, P2. Then it's a G what? 0, 1, 2, P2 plus the last one is like the G1, P of 1, G2, P of 1, and G3, P of 1. Cool. So you see, if we know what P's are supposed to be, we can solve it for G's. This is a matrix system in G's, right? And that is exactly what we want to do. So we want to find out what G's are supposed to be, after all, in the dissection. No, I'm exactly saying the wrong thing. We want to split P, because that's the portion that we want. We need this P of 5n plus 4. This is what we're interested in, which is one of the P's. 5n plus 4. So we will take P's to be the unknowns and G's to be knowns. They're coming from the Euler's pentagonal number theorem. So if we think that we know G's, we can solve it for P's. If we know P's, we can solve it for G's. And this time we want to solve it for P's, because I mean, that's what we're after. We're after this object. We want to rewrite that object, which is one of the P's. Okay? So we are after P's. Technically, we're actually after P4. So that's the main thing, but we're after the P's. So we will take it as it is a system where P's are unknowns and G's are knowns. But we can do a little bit better than that. We can actually say like, now this is just a matrix, like as you can see. It is multiplied with the vector like P0, P4, P3, P2, P1. With some switching around. Can we find what it's supposed to be equal to after that multiplication? I think we can. We just need to refer to this last thing. So let's think about the first one. So S0 are all of these pieces of GP products where you have x to the power 0 modulo 5 type exponents. So in the multiplication of these, and I know the outcome of the multiplication, what terms have 0 modulo 5 exponents? Like just one, right? I mean, the one has x to the power 0, and that's the only thing that we have. So this first thing is actually 1 and nothing else. Just that. We know the multiplication. Now we're just picking and choosing what we like. What about this one? So S1 is all the things among this multiplication which has 1 modulo 5 exponents on the power, like as the exponent of x. So what exponents of x do we have here that has 1 modulo 5? There are none. There's nothing going on, right? I mean, there's just one term. We already used that term, so it has to be 0. I already wrote it by accident. But you see how this system is going to be work out. So there are no terms here. So no terms with x that has an exponent which is 1 modulo 5. So there's nothing. This guy, the same deal. So what pieces of this multiplication have 2 modulo 5 exponents of x? Well, I look at the exact multiplication, there's nothing. So it is 0. So it is also 0. So this one is also 0. So we really have a matrix filled with g's. Okay, so start with g all the way to g cube here. We multiply it with these p's that we're trying to solve. So this is p0 to p1, and we're trying to solve it to 1 0 0 0 0. This is really a linear system, and we're after these things we have an understanding where all the pieces are coming from, but we will over time we will find the exact formulas. But the way that we want to approach this is we want to solve what P4 is. So for that, we are actually solving all the P's. All right, cool. So let's call this matrix to be D, the matrix of G's to be D. Well, one thing that we can check is, can we find the determinant of that? So D itself is given as G of I minus J. So this is the matrix of that. Am I correct in this? So 0 0 is fine. 1 is, so I and J, I think it should be J minus I. But still, it's just the GIJs. J minus I comma J. So at first it is J plus I is also okay, but then it will be G2 here. Not that it matters. It's just I'm going to be. I mean, after all, we don't care. The point is that D is this matrix, and we know exactly what that matrix is. We can write it. We can write it out. We're more worried about what its determinant is going to be. So B, let's write it out again. So it's 0, 1, 2, 3, 4 for G's, and then it's like just goes diagonally. So this is G1, G2, G3, G4. This is all G4s, all G3s, all G2s, G1, G1, and then you repeat. So G0, so it is G2. We know the matrix. And now we're more worried about what is the determinant of this matrix. Okay. So determinant. All right. Now, another trick, and this is actually the trick of how this dissection is being made. So from like the full sum, you want to dissect it into 5 pieces, right? The way of doing that analytically is you include the root of unity. So you put a root of 50 root of unity. So some things stay real, some things go in the first direction of the root of unity, some things stay in the second direction of the root of unity. So that's how you split things. And that's where this thing shows itself. So let's define the zeta to be e to the 2 pi I over 5. So this is the fifth root of unity, right? And let's take the Vandermonde determinant. So let's take this B matrix. We can't really directly take the determinant of that, but we can get an idea of what that thing is when we also incorporate this B matrix. So this B matrix is the zeta to the JK. And yeah, J and K are between 0 and 4. I wrote it that wrong. Here it is just, I and J. It's either way. I comma J, 0, I, J, less than or equal to 4. Oh, that is the I, is the complex I. So that's, I should say that J and K. Thank you. Yeah, we are dealing with the root of unity. That's why I should use J and K. I'm following the text. And there was a reason why I put it that way, but yes, the reason is this I is the complex root of unity. Cool. So we have the Vandermonde determinant. So it is just that we have 1 and 1, 1, 1, 1, then zeta, 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 and it's pops, right? And we know what the Vandermonde determinant is supposed to be. It is really simple, and it's really useful for us that it's in the Kuboheimer form. All right, so we're after this now, but we don't know how to solve it. So instead, we pay the price, we include this Vandermonde determinant, and we will look at the determinant of D times B. And it's a 5 by 5 system. Jacob is gonna say that we need at least 98 multiplications, maybe less. But the best we have is like 98 right now. So what we have is this sum. J from 0, no, I shouldn't use I. J from 0, G of H minus J, and zeta of JK. So in that, now that I remember that we're indexing from 0, we can also go back and do the correct indexing. So D is the matrix of G of H minus J, and so it is 0 and 0 at first. Then it is so it is J comma H, right? So then it's like 1 minus 0. Yeah. 2 minus 0, 3 minus 0.
0 minus 1, 2, 3, 4.
I don't want to change the order of these things. Do I want to change the order of those things? No. If it is plus, it's not going to matter for the first one. If it's plus, is it going to work out? So yes, this is 1 now. That is 2. That's 3. That's 4. That's fine. This is fine. What about this one? 2. Good. There's 2 plus 0. 2 plus 1. 3 plus 0. 3 plus 4. I think this one is working out. So it's H plus J then. Why isn't H minus J working? I need to put H minus J here though. Not that it matters. If we change the, because we're dealing with the determinants, not that it's going to matter like too much at first, but because we're dealing with determinants, I don't want to change the order of rows, right?
Probably we should have the same order for the F and for the P.
Yeah. That's what it is. That's exactly what it is. Yes. So we can have it H minus J if you write it as P0, P1, P2, P3, P4. So let's write it that way. We know what we're dealing with. The actual matrix that we want to deal with is when we have the columns associated with the columns associated with P0 first, then P1 the second, P2 third, and P4, P3, and then P4. So the first column is not going to change. So it is just G0, G1, G2, G3, and G4. The second one, we will deal with the things with P4. So it is G4. So it is the -1. Yeah, it's the minus J. So this one is, I need to make one modulo something out of it. So I already have that. So it's G0. Yeah, so this is G1, G2, and G3. So it's a cyclic. Yes, exactly. So it's cyclic shifts. Yeah, perfect. Okay. We're trying to solve this system. D is supposed to be that. Okay, so P2 is going to be 0. So this is G3, this is G2, this is G1. Cool. So 3 went to the top, then everything got shifted down one time. So G4, G0, G1, G2. So 2 went down, so it is G3, G4, G0, and G1. G1 went down, went up. So it will just go down that way, G2, G3, G4, and G0. Good. Now we have the correct indexing as well. So we're dealing with the G of H minus J's for H and J to be less than or equal to 4. And I will just go back for one page, for 1 second, and change the name of that matrix. So this is, of course, the same related thing, but the way that we're writing is just a little bit different. This is not what we're after. We just reorder things. So when we're multiplying D with P0, P1, P2, P3, P4 as a column matrix. Before we were multiplying it with some other order like of that, which is fine. Yeah, the same deal, but so that we stay the same with the text. So that we stay true to the text. Okay, D times P. We define the Vandermonde matrix. We know how to take the determinant of that. We now know what D is completely and the product of these things. And we are after the determinant of that. The product looks this way. So if I were to take this element to be the H comma K, so if I want to do the multiplication first and understand what this multiplication is, maybe using the structure of this G, I can combine these terms and see what it is supposed to be. So let's write this AH comma K. That is the sum from J being 0 to 4 of G of H minus J, and this root of unity at JK. Cool. Now, well, what I can do is I can multiply and divide. It's a minus HK. Okay, right? Nothing too bad. So I can take this term out that is not related with the sum. HK. J from 0 to 4. Then we would have G of H minus J, depending on X, and a zeta of J minus H of K. So the indices are basically just negatives of each other. So if we are dealing with the residue class S here, because the G was a dissection of this, G was a dissection of the Euler pentagonal number theorem into the residue classes. So if we're dealing with the residue class S in this portion, the zeta's root is minus S. It's the power of that is negative SK. All right. So this portion, at least, only depends on the residue classes. We know how these things split. Cool. Now let's play with this even more. think about this piece, g of sx. That is the inner piece, nothing really special. So zeta of minus s of k. If you think about this guy, this is sum of things x to something which is plus s. It's s modulo modulo 5. That's what I mean. So the exponent here, exponent of this sum, the exponents of the x's are always s mod k, s mod 5. This also has that s mod 5. So maybe I can just pull this zeta in. And that needs some faith in me. I hope that you have that much faith. So I will just say, if I were to put this x and tag along this minus k with that, I would have the same thing. Now, why? So the residue classes match, so s is good. At any iteration of this x, I'm gaining a step of 5, but the root of unity, the 50 root of unity, with any power 5 is just 1, right? So always we're not changing the residue class. That this needs that s, that guy has the s, plus maybe so many 5s, but those 5 exponents, like the power 5s, for the residue, like for this root of unity, it is always 1. Is that okay? Convincing, hand baby. I hope it is convincing enough that this already has that residue class that s we need in the powers, and then we take it in. So once again, g of s of x times the zeta of minus sk is this guy, something, 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 x2. Here we have an s plus 5 times m, whatever that m might be. And outside of that, we have the zeta of minus sk. But technically, what we're doing is, well, we're just saying this could have had as many 5m's as it needs to, because I mean, this is a root of 5th root of unity. So any multiple of 5 in the exponent doesn't matter. It's just going to be 1. We were just kind of pushing it here. And then combining this s portion into x. And that gives us that g of s x zeta of minus k. And as I was saying, this is like the really that insertion, the forceful insertion of the root of unity to split everything up, right? Because this gs was the earlier pentagonal number term when you sum up all the possible residue classes. Now we also included the root of unity to just split it 5 ways in complexes. All right, cool. Now let's remember what this a was supposed to be. So a was the thing that we're looking for. That is the multiplication here in the matrix, in the 5 by 5 matrix. So we have a multiplication of 5 terms, addition of 5 terms. Then we multiply these things. Then we edit these two. Now we found a new way of writing that with a factor in front. But I mean, who cares about that factor? We can take care of that later on. So once we write it back again, you see that we actually are not so far from what we know before. So a of h comma k is that front factor zeta of hk, which was needed. Then we have that 0 to 4, the sum of g of s. Instead of having g of sx times zeta of minus sx, we have g of s x times zeta of minus k. Cool. This was a lot of work for a good reason. Remember this guy? With only the x, not x and zeta. With only x, this was supposed to be x sub infinity. it was the Euler's pentagonal number theorem. We knew the product representation. Now this is just that x is replaced by x times the root of unity. So we actually know how to turn this into a product this time, because we're summing up over all the residue classes. This is zeta hk. It sounds like I wrote kk. So it's h and k. Then we have this product of not k, the product of I, or even just I will write it this way. So E of x zeta minus k, or in terms that we remember, so hk x zeta minus k, comma x zeta minus k sub infinity. So we now have a full infinite product for this AH case. Cool. Now, this was, if you remember, this AH case were a part of this multiplication D times V. These were the AH case. And we were trying to take this determinant. We can take this determinant separately as well, because we were after this determinant of D after all anyway. And that is going to be the determinant that we have from 0 to 4 of this e's of x zeta minus k. So these guys, and when you multiply all of them from 0 to 4, we end up getting a 0 modulo 5 residue class. So this becomes 1. We don't need that. Times the determinant of the Vandermonde. Yes. Okay, then we can clear out this Vandermonde. Vandermonde was used to insert this root, which gives us the determinant that we need. So the determinant of D is this product from 0 to 4 or k, let's say, of these E of x zeta minus k's. Let's write it out. This was the product. So this product is actually coming from this. Good question. Let's check that again. So one thing we have is like we can split this into two ways. So this is determinant of D times determinant of D, and we're after this guy, right? Come on. So now we have this. Now we know that they're all these infinite products. So the product of that guy, product of dV, is the product of these zeta hk's and E of x zeta hk's, or h and k from 0 to 4. Come on, brain. Okay. If I were to write it out, I think we're going to see it. So let's write this out. Yeah, that's an important step. Let's not skip over that. Oh, but after, yeah, this is what we're going to get. So let's write this out once again. D times V. We are sure, like we're happy that this is the zeta h times k, then E of x times zeta of minus k, where this matrix is over h and k from 0 to 4. Let's do the backtracking once again. That we have the rows to be h and columns to be k. Not that it's going to matter because we have the determinant, but over here, D was H and J, and V was J and K. So we got rid of the mid indices. So we have rows in H, columns in K. Okay. Let's write this out. H and these are all zero. So this is E of X. Then we have H is zero. So that guy is not even. H is zero still. K is one. So that's still one. And then we have E of X of minus one. E of X of minus two. E of X of minus 4 on top of zeta. Here we have the zeta H and K, so it is 1 and 0. So again, this is nothing here. And K is that, so it is E of X. So here's the first zeta, which is E of X Q to the 1. So this is 1 and 2, so this is 2 E of X zeta minus 2. And the bottom one is E of X. Then this one is 4th row. So H is 4, K is 1, it is to the 4. This K is 1 again, X to Q minus 1. Now, let me just hide this. Let me hide the right thing. And let me see what we're dealing with. So essentially, I want to say that this is the Vandermonde determinant times the product of these. Of course. It makes perfect sense now. Once you write it down, you see, look at the first column. It has all E to the X's. It is a constant. Play it out. So from the first column, I can take out this E to the X. I mean, of course, I need the absolute value of that, but I will put the absolute soon. Then from the second column, I can take out all these E to the X zeta negative ones. It's a constant. Then I can take out all these X to the zeta minus 4 all the way there. Then what is left is the 1, 1, 1. The root is the Vandermonde determinant. Cool. So now, thanks for keeping me honest. Thanks for not brushing over that. So it's good. Now we know that we have this product plus the Vandermonde determinant. That's okay, right?
Yes.
Perfect. I'm glad that we wrote it out. But I mean, as it gets technical, I mean, it's just becomes more likely that I brush off things, but we're close. We're close to going back to the partition function really soon. So from this calculation, we found out that the determinant of D is this product that we were looking for, this product of E to the X zeta minus K's, from K being 0 to 4. And because Vandermonde determinant was just 1, okay. And this E was this X zeta minus K, X zeta minus K to the infinity. So it's the infinite product. So let me write it as an infinite product and switch the order of products as well. Again, if you're worried about convergence at all, just keep your X lower than size lower than 1, and everything converges absolutely. Everything converges uniformly, absolutely. Everything is good. You can do any trick that you like. So M from 1 to infinity. This is the product that will come from Pohammer. Then the product that we have, K from 0 to 4. And now I have 1 minus that minus K M and X to the M. All right. Let me just write that in color maybe, so that you know what it is. So this portion was that Q Pohammer X zeta minus K, X zeta minus K, infinity, and zeta is the root of infinity, fifth root of infinity. All right. Now, let's recall what we were after. What we are really after is these 5m plus 4 terms in the partition function. So p of x was the original partition function with xn. We dissected that to p4 was the most important thing for us, the piece that we were interested in, and p4 was this p5n plus 4, the thing with the congruence condition that we observed, and on the top we have 5n plus 4. Okay. Now I want to go from these to D to that, and D was the matrix of G's, a lot of G's, a lot of G's. When we multiplied with the P0, P1, all the way to P4, it was giving us the solution 1, 0, 0, 0. I mean, 5 rows, not like nothing crazy, 5 rows, 5 by 5. So from this D, after all, I will try to hunt down what this P4 is supposed to be. So for that, I also want to understand like what pieces of this product, infinite product, stays in the real values, stays in the complexes, like how are these products like appearing? So can I simplify this nested product? Because from this point on, we will work from D and try to get that P4. So let's try to understand what these products are supposed to be. So one thing, a simple case, if m is 0 modulo 5. If m is 0 modulo 5, then I'm already raising the root of unity to some 5th power. So that's already 1, right? Then I have 5 copies of that. Then I have the infinite product. So what is that product then? If this is the case, this product that I have on the inside, k from 0 to 4 of 1 minus the 5th root of unity minus km xm is, well, just as we said, it is this guy, because I'm raising that to a power of 5, is 1 minus xm, or k from 0 to 4. Or it is 1 minus xm to the power 5. Just trying to understand better, right? So if m is congruent to 0, I can replace that nested inner bit with this factor, 1 minus xm to the 5. What if it's not? What if it's not congruent to 0 mod 5? Then what are we gonna have? Then it actually simplifies even more. 1 minus zeta minus km xm. How should I make sure that we see this? Think about xm. When you multiply things over k, you will always get 1 plus the k being first copy of this minus m, then k being the second copy of this minus m. And they're negatives, but I mean, it's the signs are going to mesh up. Nothing to worry. Then the sign is going to be like this minus third copy of m, and the fourth copy of m. Well, actually, it's always going to be with negative, but it doesn't matter. So these are going to come, and we have a 5th root of unity. So what is that sum on the bottom? This will come with xm. 0 is the 5th root of unity, right? So in each combination of these, we will always have all the combinations of the roots of unity. So they will always cancel out, except for 2 cases. One is when you always have just 1. And the other is when you always have this ending bit. So 5 m's, which is minus x to the 5m. If we always take that, then these guys are being multiplied. And you sum up to 0 to 4. So it is triangular number of 4, which is 4 plus 5 divided by 2, 10. So fifth root of unity raised to 10 is just 1. And the minus comes from that and the fact that we have 5 terms. Cool. So we have two possibilities. Either m is congruent to 0, then we have this nested product turning into this factor with 1 minus x to the m to the power 5, or it is not 0 modulo 5, and then this inner product becomes 1 minus x to the 5m. No, perfect. That's really what we need. So then this guy becomes, the product becomes that we have m from 1 to infinity, that outside product. And it is, I think that 5 is written as an extra. So 1 minus x to the m to the 5, if m is congruent to 0, or because it's a product, I'm just splitting that, or I have m from 1 to infinity. This time m is not congruent to, oh, okay, yeah. So m is congruent to 0 here. If m is 1 from 1 to infinity and m is congruent to 0, then I have x minus 1 m to the 5. That is what we said here. And if I have the product from 1 to infinity and m is not congruent to 0, then I have this 1 minus x 5m. Okay? Technical, but we have it. Now we actually have what we want to have. So once again, let me write this. D, it is the product. M from 1 to infinity, m is congruent to 0. Then we have, then we have 1 minus x to the m to the power 5. That was how the simplification was going on. And we also have m from 1 to infinity, and m is not congruent to 0 modulo 5. So this is 0 modulo 5. Then it is 1 minus x to the 5m. Cool. Well, if you don't mind, I want to change this a little bit. So it says m is 0 modulo 5. So m is divisible by 5, right? Maybe I can reflect it in the exponent. So if m is divisible by 5, so m itself is 5 times the new m. So if I put a 5 here, would you believe that this is the same thing? So instead of x to the m, I have x to the 5m. So the m's are always divisible by 5. And over here, in this case, I almost have everything, but I just don't have this m congruent to 0 case. So if I were to fill that in, if I were to just get rid of this condition for once and multiply it in, multiply those factors that are missing in, can I just divide it out? Can I understand what I'm supposed to divide out? So I need to multiply in when m is 0 modulo 5. So m from 1 to infinity, 1 minus x, 5m. M is 0 modulo 5. This is what I want to add so that this guy becomes a whole. I can drop these conditions. But for that, I need to also divide the same deal. So I need to divide m is 1 and m congruent to 0 modulo 5. 1 minus x to the 5m. Is that okay? Well, here the good thing is, yeah, we put these together. So I can drop the condition on the residue class of m. So we got the first one anyway. So it is 1 minus x to the 5m to the power 5. I will use the same trick over here just in a second. Over here, we have the product m from 1 to infinity. all the non-zero residue classes mod 5 is coming from the first one. All the 0 modulo 5 classes are coming from the second one. So it is everything 1 minus x to the 5m. That's how this combines, divided by product m from 1 to infinity. M is congruent to 0 mod 5. 1 minus x to the 5m. Again, I want to get rid of this extra condition. I want to have full product, so I can write them in the e function, right? If I were to get rid of that condition, how should it reflect to the product? Exactly. So if m is divisible by 5, then I can just pull that 5 out. So it will be 25m. And I will get rid of this. So there's a lot of renaming going on, but I mean, I kind of hope that you are seeing it through. Okay. So what do we have on the top? We have the full product with x replaced by x5, 5 times here and 1 time there. So we actually have e to the x5 to the power 6 on the top, divided by e to the x to the 25 on the bottom. I will need to jump a little bit back, but you see this is not too far from what we want to solve. And we have already done all the dirty work, so we will solve it quite closely, quite easily now. I'll need to jump back, jump back, jump back. We're interested in this P4. And the term that we gave in the first thing is that we need this e to the x5 to the 5. So one of them will cancel at some point, that e to the x to the 6. So I'm expecting when I can finally get that P4, the capital P4, I'm expecting to get rid of that x to the 25 piece and one of those x to the 5s. And that 5 will pop out somehow. But from now on, we will try to solve that P4. Because we have already done the deed. We have already finished the matrix determinant of like the matrix D. And now, from this formula, and knowing what D is supposed to be, we will try to find what P4 is. Because that is really what we're interested in. So can we calculate what P4 is if we know what D is? In general, not. So we have this D times this P0, P1, P4 is equal to 1, 0, 0, 0, 0. Right? Yeah. So we know what D is supposed to be. We know what determinant of D is supposed to be. It is e to the x5 to the 6, e to the x to the 25. If I want to solve P4, what should I do? Think about the multiplication. It comes down to like I'm solving P4. We can do it in multiple different ways. I will do Cramer's rule. Is that okay? So with Cramer's rule, this P4, the last column, would be the fourth minor of D, which I will write in a second. It's just we're going to ignore the fourth column and fourth row, divided by the determinant of D. Cool. And this fourth minor is supposed to be, it's also a determinant, so maybe I should just put it this way. And that is, I'm really ignoring the last row and last column. G0, G1, G0, G4, G3, that's G2, G3, G4, G3, G2, G1. So G1s are going that way, divided by this star. Cool. All right. So if we can evaluate what D4 is supposed to be, and that's the last bit of the technicality, if we can evaluate what D4 is supposed to be in X, if we can find the formula, then we're hoping to see that the theorem is going to come out. That 5 is going to come out as well. So let's try to figure out some pieces of this P4, D4, and understand what it's supposed to be. Okay. So D itself was coming from this G function's multiplication with the P function. I need to really jump back, and I apologize. There's some backtracking going on. So there's a G function, there's a D function, and D itself is coming from this P of S multiplied with G of S. And G of S is the Euler pentagonal number term, which is like the 3n squared plus n divided by 2 pieces. And P of S is the P of 4 is what we're trying to solve. So okay. After all, right now, I'm trying to identify what this matrix is. So I will try to make sure that we understand it well and we can get rid of pieces. So D is related with G and P, with GSPS, multiplication of those. It is related with that. So for D4, I want to understand like the piece of G, where it has the pieces of G. All right, let's recall this G itself. It is the sum of -1 to the n, q to the 3n squared minus n over 2. That's the Euler pentagonal number term. With S, I'll just have this this 3n squared minus n over 2 is congruent to S modulo 5. So let's see if this exponent that we have can ever be 3 or 4, for example. So if I want to do the elementary number theory portion and say 3n squared minus n over 2 is congruent to S mod 5, that is the condition on the GSs, nothing else. This is the same thing as saying that, oh, come. 2s, yeah, it should be 2s. I wrote something wrong, which is all right. So we can just clear the denominators. 2 has an inverse in this field. I mean, it's a field, so it has an inverse. So multiply everything with 2. It is 2s mod 5. And then what I want to do, I want to multiply everything with 12. So it is 36n squared. I mean, by 12, it became 24s mod 5. And after all, you can turn it into 6n minus 1 to the power 2. So 24s is minus s modulo 5. And I need that plus 1 here. So there's another plus 1 there. Minus s plus 1 mod 5. Cool. Now, last bit. So if 3n squared minus n over 2 is going to be s modulo 5, then 6n minus 1 squared should be minus s plus 1 modulo 5. We look at the residue, quadratic residues modulo 5, which are only 1 and 4. So this can only be 1 and 4 for us to have an answer in n, for us to be able to find an answer. So if this is 2 or 3, if this minus s plus 1 is 2 or 3, we won't really have any answers. Am I doing right? So this, yes, plus 1 minus 1, 4. Yeah, so if s is 4 modulo 5, we don't have an answer. And if it is 3, then it is like plus 2 minus 2. So it is s is 3 modulo 5, we don't have an answer. So I solved it. I solved this system with the s. So if this thing is going to be congruent to s, it shows that this thing squared must be minus s plus 1. So that thing is a quadratic residue modulo 5. And the two quadratic residues, non-zero quadratic residues, modulo 5 are 1 and 4. So if this is either 2 or 3 modulo 5, we don't have an answer in n. So that's what I meant with. So I put it in 2, minus s plus 2 is 2, minus s plus 1 is 2, so minus s is 1, so s is 4 modulo 5, which means there's no n that can satisfy that. Or the same deal, minus s plus 1 is 3, so s is congruent to 3 modulo 5. S is congruent to negative 2 modulo 5 or 3 modulo 5, and there's no solution in n for that, which actually says that G3 here is 0, and G4 here is 0. Because there are no n's that can contribute to these G3s or G4s. That will actually have a solution where we dissect this. We just simplify the matrix a little bit. Everything clear? Or too technical now? It's just things are happening and we don't know why. So here's the matrix that we know the determinant of. And over here we had, now we got rid of these G4 and G3. You can ask it again.
Because you're ignoring the last column and the last
I believe so. It should be that way, but I mean, it's this matrix. So if there's a transposition, I'm pretty sure it's the same determinant at the end. And if there's a transposition, if I'm making a mistake, apologies for that. But what we learned is that on this top part, we have a tiny triangle on the top and the bottom to be zeros, because G4 and G3 are supposed to be zeros. So these three elements on the top became 0. These three elements on the bottom became 0. So we got a diagonal matrix. I mean, not fully diagonal, but diagonal on the back and forth. Cool. Okay. Now let's write that once again. Please. Yes. All right. D4. I think the determinant of that is G1 and a G1 and a G1 and another G1. Then it's a G0 on top of it, G0 on top of it, G0 on top of it, 0, 0, 0, G2, 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 0, 0, 0. GS is the Euler pentagonal number term again with the x to the 3 n squared minus n over 2 from negative infinity to infinity plus that that 3n squared minus n over 2, that exponent we have needs to be congruent to s modulo 5 with the extra condition that we have split that into residue class modulo 5. What we did is we solved that n squared minus n over 2 congruent to s mod 5 and learned that s cannot be 3 or 4. So they were giving us contradictions. So that's how we got these zeros. So to recap, we can also now solve for s equals 1. Why not? We have the condition anyway. So if we were to solve that s equals for 1, we would end up getting like the thing was when we solved it, I don't know why we got that. Yeah, when we solved the formula with s, we end up getting a 6n minus 1 to the power 2 is congruent to minus s plus 1 mod 5. So if we solve it with s equals 1, this is the same as solving that the residue, quadratic residue is 0. So this thing squared is 0. That thing itself is 0. 6n minus 1 is 0 modulo 5. Or 6n or n is 1 modulo 5. Right? Or n itself is 1 modulo 5. And well, if that is the case, why not just plug it in here and see what we're going to get? So let's see that g of 1 of x. I'm really like getting our hands dirty. I am just saying that n needs to be 1 modulo 5. So in the Euler pentagonal number theorem, I'm just plugging in, instead of n, I'm plugging in 5n plus 1. So all the n's that are 1 modulo 5. And it is x to the 5n plus 1 to the power 2 times 3 minus 5n plus 1 divided by 2. Okay. I will skip some steps and even leave it as a homework here. But a couple of simple steps. This is a theta function. This is Jacobi. This came from Jacobi triple product identity. It will come back to the Jacobi triple product identity anyway. You simplify that, and you see that you get minus x times this sum, -1 to the L. And yeah, so this negative, then 5n is the same as n. So change it to L if you like. X to the 25 coming from the 5 squared. And then on top it is 3L squared plus L over 2. So it is again the Euler pentagonal number theorem once again. Negative infinity to infinity, this time on L. And this is minus x times e of x to the 25. So that x to the 25 that we wanted to cancel, it is coming from that G1 at the very least. Cool. Now we know that G3 is 0, G4 is 0, G1 we have a formula for. So now only if we can understand what G0 and G2 is, we can solve this determinant. And that is basically the end of the thing. All right, let's write that determinant. The force determinant is that G1's going down, G0's here, and G2's here, and nothing else, all the zeros, is G1 to the 4, right? Minus 3, G1 to the 2, G0, no, G0 and G2, yeah. That combination plus G0 squared and G2 squared. So we now know what this portion is. If we can identify the other two, we're going to be good. Right. We finally came to the H function. And we're almost there. We're almost there. I can see the tombstone. I can see the tombstone of the proof. So we're happy. I mean, at least I'm happy. Okay. This time, let's look at e to the x cube. Remember, this was that formula with the 2n plus 1. That was the H formula. So on the back of our head, we have this, and we will use it in a second. But if we were to just stick with the g's, this is that sum of from 0 to 4 of the GS's to the power 3. We already know G3 equals G4 equals 0. That is also something that we have gathered. So this is just G0 plus G1 plus G2 to the power 2. Cool. And now let's use this other formula, which is that this 2, 3. Yes, exactly. I mean, I saw 2s. Thank you. So this is the same thing as that other formula, which was the h of x, or the sum of hs's from 0 to 4. And this is this formula. So it is -1 to the n to n plus 1, x to the n squared plus n over 2, and n from 0 to infinity. So this one is one-sided. Cool. Okay. Well, let's make terms. So we have 0 modulo 5 exponents here. So these are xm 0 modulo 5. These are xm 1 modulo 5s. These are xm 5m plus 2s. So, and 3 combinations of them, right? When we combine them. So we can try to identify them with with this side. We know the exponent here, so we might as well solve it that way. So let's say we have n plus 1 over 2 being congruent to s, whatever that s is supposed to be modulo 5. So you solve it again, a tiny bit of work, but I mean simple work. It is 2n plus 1 squared is equal to congruent to 3s plus 1 modulo 5. So what does it say? We can try to extract stuff from this. For example, if you were to plug in like s equals 2, if I were to plug in s equals 2, I'm dealing with h2 here. Right? Those are the things that have the extra condition. If s equals 2, I would end up getting this 2n plus 1 to the power 2 is congruent to 6 or 6 plus 1, 7 or 2 modulo 5. So can you find any n so that the square of that is 2 modulo 5? No. Which says that h2 is 0. Right? We could have done it in the beginning, but I mean, we're doing it now. That's fine. So h2 is apparently completely 0. But what is h2? Can we also find what h2 is supposed to be from here? We are going to combine 3 things and make it 2 modulo 5. And we know the first one contributes 0 modulo 5, the second one contributes 1 modulo 5, and the third one contributes 2 modulo 5. What do you think? So one possibility is that you collect that 0 modulo 5 with 2 1 modulo 5s, right? So h2 from that multiplication is the same thing as g0 times g1 squared plus the other possibility is that you collect your 2 modulo 5 right away, and then you collect 2 0 modulo 5. So g0, 2 and g2. Okay. And this is 0. We already solved that. So this gives a relation between G1 and G2, and including G0, of course. So this is saying us, tells us that G1 squared is minus G0, G2. So G0, G2, we can plug that in and write it in G1s. If you were to write that, so this is a positive G1 to the 4. Then this is, you plug that in again, this is positive G1 cube, I believe. Am I correct? So this is G1 to the 4th. This one is also G1 to the 4th, but there are, so yeah, there's 1, then there are 3 coming from here. This is plus, yeah, so let's write it. So the first one, I didn't change it, G1 to the 4. I'm plugging that thing in. Yeah, we got our 5. That's what we were looking for. We got G1 to the 4. Now we plug in that G0, G2 with a negative. So it is plus 3 G1 to the 4 and plus G1 to the 4. Good. So this is, after all, apparently this determinant is 5 G1 to the 4. So we get that factor of 5. Perfect. At the very end, now let's just combine everything that we know. Okay. This P4 that we were looking after was the determinant of D4, or like the, I wrote it interchangeably, but I mean, this is determinant D4 divided by the determinant of D. Now we know that the determinant of D4 is 5 of G1 to the 4. And on the bottom, we also know that this guy is e to the x to the 6 or x5 to the 6, it doesn't matter, divided by e to the x25. I think there's a 5 here, but I will check it just in a second. Yeah, there's a 5. So we wrote them down. Let's take another step. We figured out what G1 is supposed to be. It was minus x e x to the 25. And now we have that to the power 4. And this is divided by e to the x5, 6 divided by e to the x25. Cool. Now we can just take it on the side, like just put it up. And it is 5 times x to the 4, e to the x25 to the power 5, divided by e to the x to the 5 and 6. Finally, and over here it was, once again, let's remember what this is. This is p of 5n plus 4s with x to the 5n plus 4s. Now, all the way around, that x to the 4, that x to the 4, they will cancel out. And this is a polynomial. This is a function in x to the 5. This is also a function in x to the 5. So after all that work, if we shrink x to the 5 to x itself, if we take that, we finally see that theorem is p of, bless you, 5n plus 4, gesundheit, xn is equal to 5 e to the x to the 5 to the 5 divided by e to x, e of x, 6. So we got our witness identity with a lot of work, but it says that these p 5n plus 4s must be divisible by 4 for all of the pn's, because I mean there's a factor of 5 on the other side. What a formula, huh? Not the simplest, but I mean we got it. And there are corollaries to that. I mean the reason why you would want such a thing is, let me write just a quick corollary, and maybe the following term, not to prove that, but the next corollary to this is you can, using this formula, show that p of 25n plus 24 that lies in the same arithmetic progression. So 5n plus 4 is like it's a super sequence of this. But these guys are divisible by 25. And the way you would approach that is you would take your p 5n plus 4s, the things that are divisible by 5, you divide them with that. You look at that generating function, multiply it with this e of x 5 to the 4 to show that this identity is true. So e of x to the 5 or 4, e of x and e of x to the 5. And use the Fermat's little theorem, modulo 5, to pull that 5 in, right? Fermat's little theorem was saying that you can just take the exponent outside to the inside, and that would give you what you need, basically. So you pull that in, e of x, e of x5, e of x5, 4, so you can cancel like one of them at least. And with that, you can just look through and show that these coefficients, I mean, every second term also satisfies this recurrence. Another theorem, this also due to Ramanujan. Maybe I can write the proofs of these two. The 7n plus 5, we know it was divisible by 7. The generating function of these can be written as 7e of something, not that that is important, I will write it in the notes, plus 49 of something. So you can also show that the divisibility by 7 of these coefficients using the same technique, but with a larger system that you need to solve. So, I mean, the question becomes the thing that Jakob asked like last time, like how did people come up with this? I don't know. Would I be able to come up with this? presumably portions. I mean, but I don't think I will be able to put it all together. I haven't just, there's like multiplication with 12, solving the linear system's pieces by Jacobi triple product identity. A lot of things are being involved, but it's just a lot of determination that they got these witness identities. Right? It's a really nice term. So as I was saying, the new modern version of this technique of finding a witness identity is done by modular forms and modular space, and a good chunk of that research is happening in RISC. So people at RISC are actually like really good at finding a modular space with a certain weight where you can write your suspected generating function from elements of that space and then hope that you will get these witnesses to your congruence that will pop up in the coefficients. Yeah, so, and I even believe that right now, as we speak, Nicholas Smoot and Sylvie Radu are given a talk at RISC on top of on these topics. Yeah, cool. So that's it. So this brings us to the end of the congruences portion of partitions. And next time we will do asymptotic, and that will be the last class. Cool, thank you. It's fine, I appreciate it, but
Yeah, the proof,